Older than the dinosaurs and bigger than blue whales, they turn sunshine, air, and water into the world's finest building materials. And they even keep the planet from choking to death. They're trees. We take them for granted. But what you don't know about them will amaze you right now on How Stuff Works. Trees are among the oldest living organisms on Earth, not to mention the largest. The biggest ones are the colossal sequoias of California. Each of these giants holds enough wood to build 120 houses. These behemoths weigh a staggering 1,300 tons, or about as much as 10 locomotives. That's massive, but it doesn't explain society's ravenous demand for wood. What exactly is the real secret to wood's appeal? The world plants more trees than it chops down. It has to keep up with the insatiable demand for wood.
It's producing one of the most useful materials that we have on the planet.
Which might explain why the U.S. alone harvests 40 billion board feet of lumber every year. Enough to circle the globe over 300 times.
We're always going to be able to build unique and myriad products out of it.
It's abundant and very versatile.
Turns out, wood is the only commodity in the world that combines several vital properties into one raw material.
Wood is one of the strongest materials known to man. We can drive nails through it and fix it on site, and it's low cost.
But what gives wood the power to put roofs over our heads? The answer is found in the way a compound called cellulose combines with other organic materials to create wood fiber.
Cellulose is a polymer chain that is very strong, and it is wrapped around that cell wall in such a way that the strength of the material is imparted.
To make cellulose, trees breathe in the CO2 other creatures breathe out. Sunlight breaks down the CO2 into carbon and oxygen, which bond with hydrogen and then multiply to form glucose. String together 10,000 glucose molecules, and you've got a long-chain polymer, cellulose. And if cellulose makes up the meat of a wood cell, then lignin forms the bones.
That's what gives a tree the ability to stand up. If it didn't have cell walls, it'd be a pile of jiggly stuff.
Together, lignin and cellulose build tubular cells used to conduct water and nutrients throughout the tree. The hollow cells make wood lightweight, and their arrangement gives wood its vertical grain and strength.
Wood is strong because of the necessity to conduct water. So water transport through the plant is occurring at extremely high tensions. And so without a strong structure, the cells would collapse. And that pays off when you turn it into a wall stud, because that strength is then conveyed along the entire axis of the board.
The cells kind of align themselves in position to carry the load and resist load by going into their strongest sense of direction, which is that tensile capacity.
A whole lot of strength. Think about it. Those slender, lightweight 2x4s are holding up your roof right now. But don't worry, because of the peculiar alignment of wood's special cells, it can hold up a lot more than your ceiling.
It has a very high strength-to-weight ratio, exceeds steel, concrete, aluminum, all the other metals.
That's right, steel. Pound for pound, wood is actually stronger than the metal that holds up the Golden Gate Bridge. And all it takes to create it is some dirt, some water, some air, and some sunshine.
It's hard work. It's really hard work.
We use a lot of trees. The good news is that trees can grow almost anywhere, from the Arctic to the rainforest. The bad news is that trees can grow almost anywhere. Like on the edge of a mountainside, too steep and isolated to be reached by road. Which means when loggers want those trees, they have to get them out by air.
What you're asking the pilot to do is pick up a near max load in rugged conditions in the mountains with trees that are over 100 feet tall and fly it at the maximum safe turn time to the landing 200 times a day. It all becomes sort of a synchronized dance.
Basically, it's like the little mule that can do it.
The work begins when blocks of forest, like this one outside Eugene, Oregon, are auctioned off to logging companies. Trees ready for harvest are marked. Then crews armed with chainsaws hike into rugged terrain and go to work.
Come on. Oh, you gonna do one more?
Cutters judge the lean of every tree to predict where it will fall. And here's what's crucial: sawing the tree so it drops without snapping in half on impact. That means felling it away from other trees and rocks. But cutting the trees down is just the beginning. With no roads, how are you going to get more than 1 million pounds of wood out?
The response I often get is, I had no idea this was possible. I had no idea that you could do this and move this much wood.
It's possible as long as you're willing to accept the risks. If the helicopter is blown off course by high winds, or if the log line hits an unexpected snag, trees won't be all that crashes to the ground.
So there's a lot of dangers involved in this job. It's a very dangerous way of logging, but also a very fun and exciting way of logging.
It's a difficult skill. It's not easily mastered, and there a lot of people, a lot of good pilots choose not to do it.
The helicopter swoops in and lowers a 200-foot line to a member of the crew called the hooker.
A hooker has to pay attention to that hook coming down. They'll get hit in the back or in the head by it.
The whole job's scary, actually.
And not just for the guy in the chopper. Mountain winds and the helicopter's backdraft threaten to blow loose branches called widowmakers down on the hooker.
You always got to look up, make sure you're not underneath trees. Widowmakers, snags. You know, we got snags. We got branches above your head.
And amid this danger, the hooker handpicks the wood ready for flight.
Here I'm putting about five logs per turn on this cell.
As many as 800 trees pile up at the log landing each day before heading to the mill.
A lot of the wood products that we harvest out here goes into many things: paper, housing, plywood, just everything.
It's the stuff we take for granted, things we use every day. But every day, men risk their lives to bring it to you. As loggers attack the world's wild forests, scientists worry that the voracious demand for timber has led the world to consume trees faster than natural resources can grow them. More than 30 million acres are clear-cut each year. That's an area the size of Mississippi every 12 months.
In some areas of the world, we are deforesting, and that is certainly an area of concern.
What happens to all this vanishing forest? Around 40% of all cut timber becomes lumber. Another 40% become chips for making paper. And the rest is shaped into furniture, pallets, and raw materials, fueling all kinds of industries.
Wood is just more versatile. I mean, it's just hard to beat.
It's clear there will always be a demand for wood. And some tree scientists believe it's possible to create a never-ending supply. How? By developing a new breed of super tree.
We want fast growth. We want to produce tons of biomass on a single acre.
That's why a new generation of lumberjack is leaving the forest and heading to the farm. Because it's here that scientifically bred strands of super trees are redefining modern forestry.
future's in the tree farms like this.
The plantations here are part of our forests of the future.
It's really hard for me to believe that I'm logging in a desert.
While maybe not quite the desert, this 30,000-acre farm in eastern Oregon is a long way from the old-growth forests. Greenwood Resources expects to harvest 500,000 trees here every year. And even with a tree falling every 16 seconds, this modern plantation should never run out of timber.
We currently have about 7.5 million trees. That's about twice the number of people in the state of Oregon.
We'll be able to harvest about 5 acres a day every day from here until eternity.
All this thanks to the Pacific albus poplar. What's so special about this tree species? It's especially easy to crossbreed and clone hybrids that grow much faster than other trees. Some can even grow 2.5 feet in height and 1 inch in diameter in a single year. In just 2 years, farmed poplars achieve heights and sizes that might take 15 years to reach in a wild forest.
The whole process of developing hybrid poplar varieties begins with a controlled hybridization program using selected parents.
And through crossbreeding, it's also possible to control the amount of lignin generated by different hybrids.
Lignin is the glue that holds the cell walls together.
It's all technically hardwood poplar, but tree scientists can vary the wood's strength by changing its chemistry. Lower the amount of lignin, the material that makes trees rigid, and the poplars shred easily into chips for the paper industry. Up the lignin, and you get stronger wood for sawing into building products.
We're picking out the particular varieties of hybrid poplar that do make good lumber.
Unfortunately, selective breeding doesn't stop the albus poplar from growing branches. Stands cultivated for lumber are pruned so each grows short, thick trunks no more than 30 feet tall. And by removing the branches, it's possible to keep knots out of the wood and produce much higher yields.
If you look on a natural forest, to produce the same equivalent amount of board feet that we'd run into a mill, you'd need over 135,000 acres. Where here you can grow that same volume on probably less than 25 to 30,000 acres.
Every day, crews cut 5 acres, an area the size of 5 football fields. To cut that many trees in so little time requires the mobile saw and gripping arm of a feller buncher.
It'll cut a 28-inch tree in just the snap of the finger. I cut down 60 trees in 10 minutes and do 5 to 6 rows a day, full rows.
After the trees drop, a skidder hauls the freshly cut timber to a dangle-headed delimber. The dangle head grips the log, then wheels move it up and down while metal blades strip away the branches. Why get rid of them? Because these logs will become construction lumber, and you don't want limbs for that.
I will line it up, just kind of eyeball it with the butt saw. You grab the tree and flip the head, and the tree will just kind of jump up off the ground and fling over right where you want it to, and run it out, cut it off, and flip it back in the pile.
When harvesting smaller poplars, it's faster to skip the saw and use a pair of giant shears instead. These tree scissors exert 68,700 pounds of crushing force, enough to cut through a car axle. They cut and gather as many as 5 trees per minute, sending whole bunches off to the chipper. This 600 horsepower beast can chew up to 3 trees at a time. And on a good day, it will create 1,200 green tons of chips, enough to make more than 37 million square feet of paper.
It's got a grapple system on it that he feeds into the back end of it. It goes through a chain, and then it goes into a big disc chipper, and it comes out and goes into the back of the truck as chips, with clean chips.
Back on the farm, the clear-cut rows are recycled back into use, ready to grow another generation of super trees. When Mother Nature strikes...
Oh my God! Do you need help?
I'm okay.
Wood saves lives. It's often all that stands between a home and imminent disaster.
See the hurricane coming in, you see the news, and everybody's nailing up the plywood over the windows on the outside.
Why is the scene repeated every hurricane season? Because wood is able to overcome its greatest weakness and morph from a round tree trunk into perfectly flat planks that are incredibly strong.
It really adds a lot of strength and stability more than just natural wood would have.
Kind of look at a piece of wood, but there's a lot more that's going into it than what you think.
The Achilles heel of raw timber is that it's 40 times more vulnerable to stress along the grain than across it. That's why you split wood with an axe by chopping into the top and not horizontally against the side.
Wood grain runs vertically along the axis of the plant. When you split a piece of wood along that axis, the cells peel off apart.
But by cross-layering thin strips of wood at right angles, the grain weaves together to create perpendicular bonds that give ordinary wood fibers super strength.
Well, plywood was developed to try and get around some of that problem with all of wood's strength being in one direction.
This may seem like modern technology, but it turns out that plywood has been used since the Gerson period of ancient Egypt, 5,500 years ago, and it was made much the same way. Thin strips of wood called veneers were glued together to create plywood, but the process was time-consuming and expensive. Then, in the 19th century, thanks to rotary lathes and improved bonding agents, plywood became one of the most affordable building products available, the first engineered wood, known for its great strength and low cost.
3/4 plywood, you gotta pay attention to everything over here. He's got a little bit harder because we gotta make sure we don't get hit.
Today, the U.S. manufactures 12.2 billion square feet every year. Most of it is for construction. The rest is used to prevent total destruction.
Did you see that? The whole house came apart.
Columbia Forest Products runs its plywood mill in Old Fort, North Carolina, 5 days a week, producing 12,000 plywood panels every day.
I count these boards in my sleep.
The plant specializes in high-grade poplar, made using one of the tallest trees growing in the southern Appalachian Mountains, the yellow poplar.
It grows straight, it grows very fast. It's a lightweight wood.
Because it grows fast, there's an available supply of yellow poplar in the forests of North Carolina. Its straight logs and low-density wood offer two more benefits that make it perfect for transforming into plywood.
It has good workability.
That means poplar logs are well suited for the radical transformation that happens inside the lathe peeler. The straightness of the log allows it to line up evenly with the blade on the lathe. And though poplar is technically a hardwood, its cells are less densely packed than most hardwoods, which allows the wood to peel like an apple. Every day, 3,600 8-foot logs meet the edge of one of these blades. That's 190 each hour.
It's a pretty amazing process.
The blade continuously shaves thin sheets, perfect for layering into plywood.
It's going to lay pretty flat for me, or we've done something wrong.
Giant lathes like this peel 46 feet of log in a single minute. And under such a high-intensity workload, the spinning wood quickly wears down the 4-foot steel blades.
To keep a good, consistent peel, they're changing blades about every hour.
The moisture in the freshly cut poplar logs makes them easier to peel. But there's always the danger of warping. That happens when wood dries unevenly and starts to ripple instead of laying flat. To prevent warping, peeled layers head immediately into the drying kiln.
It's dried down to this level in the kiln, where we basically control the drying and keep the timber straight and use it dry so that it doesn't change in dimension.
Once dried, every other layer is coated with glue and placed grain across grain in a giant press.
You want to warm your panels up, put the pressure there so you get a good bond to where when our customers get it, it doesn't fly all apart.
The press exerts 175 pounds of pressure per square inch and heats the individual boards to 255 degrees. This combination of force and heat seals the bonds between wood layers. Finally, lasers guide saws cutting 4x8 and 4x4 panels, which head onto the sanders.
You ever heard this whole saying that you can't see the forest for the trees? Well, I've looked at that and I don't see it, but you'll come across some panels that are so beautiful.
Wood grain grants plywood both beauty and brawn, but how strong is it? Facilities like Wood Research and Development in Corvallis, Oregon, test panels and other wood products to find out, one crunch at a time.
You have big machines that push and pull things until they break.
Tests demonstrate that the strength of plywood provides a life-saving barrier when other pieces of a wood home become deadly projectiles. And when used to build sturdy wall sections, it's possible for plywood to stand up against winds from a Category 5 hurricane.
So a 120-mile-an-hour wind on the face of a building can create upwards of 28 pounds per square foot. And this type of lateral load combined with the vertical loads coming down from the building are the types of things that blow over buildings.
Here's where plywood's cross-ply construction really goes to work. This stack of 2x4 boards and plywood simulates what happens when extreme winds hit the side of a single-family home. Even as a hydraulic cylinder bears down on a wall panel, the plywood doesn't break until the force simulates winds blowing 500 miles per hour. That's stronger than any wind ever recorded on the planet, and it's a technology that's an incredible 5,000 years old.
Those logs are going in the sawmill right now. I've got chestnut and white oaks here, and poplars are behind you there.
Oak, maple, hickory. These are hardwoods, but so are poplar, aspen, and even the lightest wood on the planet, balsa. And what about softwoods like pine, spruce, and cedar? So what's the difference? It's all in the seeds. Softwoods have naked seeds that are contained within cones. Hardwoods have enclosed seeds called fruit that ripen inside the flower. But when it comes to hardness, growth rate is the key influence.
Hardwoods maybe grow a little bit slower, and because they grow slower, they tend to have thicker cell walls and more actual mass.
Softwood trees grow faster than most hardwoods because they are an early successional species. Softwoods are the first to sprout following major disturbances like brush fires. And the faster a tree grows, the more quickly it gains a dominant position in the canopy. But here's what's so surprising about softwood. It's not really soft. In fact, it's plenty hard and really strong. Most construction lumber in the U.S. comes from softwood trees.
Softwood actually can have very hard wood, so it really has nothing to do with the hardness or the strength of the wood. It really has to do with the species or the families that they fall in.
Hard or soft, it all gets turned into usable wood the same way. Transforming round logs into square boards was once a back-breaking two-person job. But in 1813, a Massachusetts woman named Tabitha Babbitt noticed that half of the back-and-forth motion of a two-man saw was wasted. So she designed a circular saw that revolutionized the lumber industry by cutting wood in a single, more efficient motion.
When a saw blade hits a piece of wood, it cuts right through these cells. It mashes them out, just rips right through them like a freight train.
Logs between 8 and 16 feet enter the line, and to ensure maximum yield, laser scanners map each cut.
Got the two lasers, and they line up with two saws that move in and out. So once he lines it up, he feeds it through, and when it comes out the other end, you've got a square edge, nice square board.
Make that log make money, because you can make money by using that log right.
Because every piece of wood is valuable, the laser-guided cutting ensures a minimum of leftovers. But it turns out even those have value. All the wood scrapes and sawdust are sold to companies that press it into boards or burn it as fuel.
We waste nothing. In today's world and the market with timber values where they're at, we can't afford to waste anything.
So what about the cellulose? It's the lignin that gives wood its great strength. But what about the rest of it? All that white stuff that makes up most of the inside of a tree? That's cellulose. And while it may not be as strong as lignin, it does have a surprising ability. It's incredibly flexible. One of the ways we take advantage of cellulose is in paper. In fact, paper pretty much is flattened tree guts. The invention of paper goes back thousands of years. The Egyptians had a version called papyrus, made from a reed of the same name. But true paper, paper made from processed cellulose, dates back to 200 AD China, where it was first used as a wrapper, long before it was used for writing. And the basic way of making paper, boiling wood chips until the cellulose breaks down, pressing the goo into sheets and drying, has remained pretty much unchanged. There has been one breakthrough though: recycling.
So it's just a constant, endless cycle.
Paper fiber, tree fiber, is extremely resilient. The cellulose can be used in multiple fashions over and over again.
That's because paper pulp is wood that's transformed into a wet mush called a slurry. All of the wood strength is still there, only it's flattened, mashed, and rolled into the indispensable material we call paper. Pulp for making paper comes from both wood chips and recycled paper. The process is virtually the same either way. It just takes more energy and enzymes to break wood chips down into pulp. The process starts with bales arriving at Rock 10's pulp mill.
These are corrugated bales. They weigh about 1,200 pounds. They're the old boxes that come out of grocery stores, department stores.
To turn these old paper products into new ones, the bales must first stew in a cauldron called the hydropulper. This reduces them from a solid into a slurry.
Huge blender. I mean, 14 feet across, 12 feet deep. Huge motor on the bottom of this thing. It's a huge blender. It's just a lot of power and a huge piece of equipment.
The pulp breaks down within just 10 minutes. Then screens lift all the waste larger than 9/1000th of an inch.
Dirt, tape, sticks, all this stuff that you would see on curbside. He'll clean that out and reject it.
With the mix now purified, the excess water is drained, leaving nothing but saturated cellulose pulp. The outer wall of a cellulose particle is smooth. This makes it difficult for the particles to join. So during the refining process, tiny cell parts or fiber in the pulp must become abrasive in order to form bonds tight enough for making paper.
Fiber's like a string. They'll take that string and make it hairy. And then when it gets hairy, that makes it'll bond together again.
That's what happens here. Rollers compress the wet slurry between two bands of industrial fabric. As this slurry sandwich moves down the line, the rollers squeeze out the water, leaving just the bonded cellulose fibers. These bonds hold together single sheets of paper stretching over an assembly line that's 1,300 feet long.
As the screen on the paper machine picks up the paperboard slurry, the water is able to seep through. It's basically a filtering process, and the fiber stays on top of the cylinder, and then as water continually is squeezed out through pressing action until you get to the dryer section. At that point, then energy is added to the paper to basically boil off any excess water.
This happens in the dryer can. It's like one giant hairdryer used to wick any remaining moisture out of the paper.
Dryer can surface is around 220 up to 300 degrees on the dry end. We gradually dry the paper as it goes through the process. A little over 100 dryers on each machine. Pretty much like cooking a steak. You just gradually cook it until it's done. Comes out the other end about 4% moisture.
Now spools literally reel in single sheets of paper, stretching the length of 40 football fields.
It will be rolled up, and those rolls will weigh about 10,000 pounds.
That's a lot of paper, and a lot of trees and energy saved.
Recycling 1 ton of paper, you actually save approximately 17 trees. You don't use approximately 380 gallons of oil, and you save 4,000 kilowatts of power and 3 cubic yards of landfill space.
Almost half of all harvested timber is designed to be cut and nailed into shelter.
If you didn't have wood, you wouldn't have houses.
But why? We know that pound for pound, wood is as strong as steel. Well, it turns out that it's more than strength that makes wood the ultimate construction material. For one thing, despite its strength, wood is remarkably easy to work with.
We can saw and cut an end off of it, or we can drill it, or we can drive a nail in it. It's very hard to drive a nail in a steel I-beam.
It's something that we take for granted, but it turns out that the relationship between wood and nails is unique. And it's why so many houses are built out of this stuff, including ones built in factories. Every year, Clayton Homes in Norris, Tennessee consumes 130 million board feet of lumber, the equivalent of a 13,000-acre forest of softwood pine and spruce. And that's just one factory. Nationwide, Clayton constructs 32,000 homes every year, and every one of them is held together by the bond between wood and nail.
If you were to think about it in terms of truckloads of lumber, it would be a truck caravan stretching for 100 miles to deliver that much lumber to our home building facilities.
Clayton's 120,000 square foot floor remains constantly stocked with at least $1 million in materials. 90% of it is wood.
The lumber portion of a home that is built is approximately somewhere between 40 and 45% of the cost of all materials in a home. So to build a home, you're going to have 45% of the cost of the materials in a lumber or a lumber product.
So how do you turn a stack of lumber into a finished house? By taking advantage of the incredible bond between wood and nails. And if you want to do it fast, you unleash a platoon of workers armed with powerful nail guns. These air-powered guns may be state-of-the-art, but the act of holding wood together with nails is as old as carpentry itself.
A nail entering wood, it's a primitive fastening system. It's been used for a long time, and that it works very well.
And the reason why is because of wood's unique cellular structure. In every board, wood cells are like a bundle of straws. As the nail is forced into the wood, these cells are spread apart, but then they quickly collapse back, literally gripping the nail. Of course, it all happens in just a split second, which is good, because when you're assembling a house, every second counts.
There's no time delay, there's no waste, there's no waiting. It's a choreography at its best.
Construction of a 15-foot wide and 76-foot long section begins inside this steel jig. It allows carpenters to build a floor frame that's exactly square. The pre-cut 2x6s form precise right angles, giving the home a sturdy base. Workers have just 24 total factory hours to complete an entire wood-built home. That's like a barn raising with 250 people working around the clock. And it wouldn't be possible if wood didn't bond with other wood and construction supplies so quickly. All it takes are skilled hands and a pull on the trigger.
You got production time. Everybody wants to meet that time. You know, we build 5 of these outer casements, 5 side walls, 5 in walls in a day.
And when building whole wall sections, workers really pick up the pace when joining panels to the 2x4 studs. All thanks to the bridge nailer, the Gatlin gun of wall construction. It does the work of 9 carpenters in a fraction of the time by firing 250 staples a minute.
We know that every staple goes in the correct distance, where the right number apart. We don't use too many or too few.
The bond between nail and wood gives these sections great strength with very little assembly. Cranes hoist the 76-foot walls onto the finished floor sections and carefully maneuver them into place. The panels transform a lightweight wood-framed wall into a 4,000-pound mega panel.
One of the most dangerous aspects of the job back here in wall set, oh yeah, you don't want to have your fingers under the wall.
Of course, wood doesn't just bond with wood. When even greater strength is needed, workers apply steel brackets, locking the wall panel to the floor. This braces the vertical 2x4s, allowing each to support the load. When finally, workers attach the heavy roof sections to the wall panels.
You put the roofs on the walls and send it down the line, it's just complete in a matter of hours.
None of it would happen without wood, and the unique way its cells actually hold onto a nail. And over time, as the wood ages, that bond gets even stronger, which is why it's so much harder to pry out a nail from a 100-year-old beam than a new 2x4. Every day, the U.S. uses 400 million gallons of gasoline. But from global warming to international crises, oil comes with a host of problems. Not only that, it's running out.
We're going to improve our energy security in the country by having a domestic source.
And the question is how to find a domestic source that can provide enough energy. And it turns out that source could be as close as the nearest tree.
Wood can replace petroleum, basically.
The problem is getting that energy out of the tree and into the gas tank. The most prominent biofuel in use today is ethanol made from corn.
We use about 100 semi-loads of corn a day. That's about 300,000 gallons a day.
But that's just a fraction of the demand, and making ethanol from corn is highly controversial. Some even argue it takes more than a gallon of oil to make a gallon of corn ethanol.
A corn plant requires a whole lot of fertilizer. It requires a whole lot of equipment. So you have to put in a fair bit of energy to grow the corn plant.
Even worse, corn ethanol is made from the kernels, from food, the edible part of the plant, which means every kernel of corn that goes into making gas is one we can't eat.
There is a delicate balance that needs to be achieved between how much corn goes for food and how much goes for fuel.
Which is where wood comes in. Today's forests cover more than 9.6 billion acres, and every one of those trees is a giant storehouse of energy. In fact, scientists estimate that cellulose from 1 acre of trees can generate as much as 10 tons of biomass. And with improved processes, those 10 tons can become 1,000 gallons of ethanol, enough fuel to run a car for more than a year.
We get samples of biomass from a variety of sources, from either going out into the fields and getting samples from natural trees, to actually going into the greenhouse and taking genetically engineered and altered trees.
This is an example of a tree that was growing fairly fast. It's only 6 years old. You cut down the tree, you chip the wood into smaller pieces, and then you basically convert that wood into alcohol. And we can remove the alcohol from the vat where it's being created. Generally what happens then is they transport it to a place where they mix it with gasoline, so you get that 10% E10 fuel that you see at your pumps.
Like corn, tree leaves turn sunlight and carbon dioxide into energy. In corn kernels, that energy is stored as starch. But a tree isn't like a gas pump. All that energy is stored as a carbon-based sugar in the part of wood called cellulose.
Cellulose is the most abundant biopolymer on Earth. It's in wood. It's about half of wood substance.
Tapping into cellulose is the holy grail on the quest for energy independence. And because tree cellulose produces twice as much ethanol as corn per pound of biomass, trees could be the best renewable source of alternative fuel.
The U.S. has a goal by the year 2020 of producing 36 billion gallons of ethanol, and that would represent about a third of the gasoline that we're using today.
So why aren't we making millions of gallons of ethanol from trees right now? Because it's very difficult to tap the energy inside tightly packed cellulose.
Cellulose is put together in a way which is so difficult to break apart. It's crystalline and it's very, very solid and very stable.
And that cellulose has to be broken down to be converted into fuel. To do that, scientists are working with some of the smallest loggers in the world by developing specialized microorganisms like bacteria and fungi to break down the cellulose walls.
We're wanting microorganisms that can directly attack the wood material. We want the primary goal to be making fuel.
The real solution to making cellulosic ethanol a viable alternative to gasoline will require more than just a better microbe. It will also require a better tree. So a research team at Oak Ridge National Laboratory in Tennessee is developing breeds of trees with cellulose that's easier to break down. The ultimate fuel tree will have lots of cellulose, as little lignin as possible, grow incredibly fast, and in just about any conditions.
We want a plant that grows very fast, can survive whatever nature throws it, and doesn't require a whole lot of fossil fuel or inputs to grow.
For these scientists, the focus of their work is hybrid poplars. Poplars already have many of the characteristics of the ideal fuel tree. They're hardy, naturally fast-growing, low in lignin, and grown in vast farms for pulp. Now, by affecting the DNA, they hope to make hybrid poplars even better. But that's not good enough to solve the fuel crisis. To make the tree more efficient, scientists at the lab are taking it apart right down to the individual gene.
We need to try and understand how the genes influence the plant. Now, once we discover what those genes are and how they function, we may be able to make a modified plant where we intentionally tweaked or turned on or turned off a gene.
Scientists want to turn on genes shown to promote cellulose production and turn off those that create lignin. Through this genetic engineering, they hope the resulting tree will be the ultimate cellulose-producing machine.
A series of instruments that will help us characterize the chemistry of the cell wall, the genetic makeup of that individual, DNA sequencing, as well as the architecture of the plant.
The goal is to more than double the biomass of cellulose produced in today's poplars. If they can achieve their goal, wood, not oil, is going to be the fuel of the future.
Actually make wood into energy sources in more efficient ways. I believe that we can produce a significant amount of our fuel from bioresources.
From dinosaur food to a new source of fuel, trees have completely transformed the world. Strong, light, nailable, and recyclable. They are a miracle material that surrounds us every day, one that may still hold new surprises.
接下来，经过了200次吃尽苦头的探险之旅，麦克罗来到了蒸汽火车头之乡爱德荷州，干尽苦差事。接着播出